Okay, so welcome to the lecture series, and now we'll be doing a very interesting thing, which is to use everything that we have studied so far at one place, and that is what we call as the classic planning. So what did we study so far? We started off with something which was called as search, where given some kind of source, which could be the source of my normal grid search or source of a very complicated single player video game where you have to do a lot of things, and I was given a goal, and what I was trying to do is compute a path from source to goal. The problem really was that every time I'll give you a question, you would eventually have to program everything and decide what are good heuristic functions and program it up from scratch yourself. Of course, there are some libraries that make task a little bit simpler, but everything was dependent on how do you define your states and actions, and that was different for each and every problem. We also did what is called as the logic, wherein in language like Prolog, we said that we just defined something, we never programmed really. So we had Boolean logic, which could take in true and false and worked around everything by definitions of functions where everything was defined as a proposition logic, also to say everything was either true or false. So now what we'll do, one thing is that whenever we were dealing with something which was logic, we said everything is at the same time. There weren't actions which were changing positions, actions which were changing by any sense something in the environment. All we were doing was that given this knowledge base, what extra can we derive out of it? Now we'll combine the two things up and we will see what happens when my agent acts in a physical world and changes things around. Something which was false now becomes true, later on it will become false, number one. Number two, my agent is now not asking questions, is this true or false? It needs a sequence of action or a plan which, when executed sequentially, step by step, will lead all the way up to from the source to the goal. And that is my agenda for today. How do I go from a source to a goal? So I combine both these things up, and what I'll be doing is my states and actions will be nothing but things which are following the propositional logic, or the states will be nothing but symbols which could be true or they could be false. And by this constraint added on top of my classic search, I'll see what all can we do about it. Now, I'm personally a big believer that whenever you say two things are being fused together, you must intuitively understand how is it better than the first option and how is it better than the second option. So let me very quickly put that up. Search compared to classic planning, we are adding a constraint that is usually bad. Earlier, my variable's position could be anything as long as it was discrete. More technically, the states need not be discrete, the actions need to be discrete. So my variables could be anything, 1, 2, 5, A, B, C. Now I'm putting a constraint that it has to be a propositional logical variable, or it can only take in a true, a false, or an unknown, as we'll talk later. How does it help me? Of course, it helps me in writing excellent heuristic functions that are not specific to the problem. If I change the problem, the heuristics are not gonna change. And just like constraint satisfaction problem, where we had excellent heuristic irrespective of what domain the problem is coming from, we'll have excellent heuristic that will not be specific to whether you are doing the 8 puzzle problem or the traveling salesman problem or any other specific problem. Compared to logic, yes, logic per se did not have time factor attached to it. There is a generalization of logic wherein you could have the time factor attached to it. However, the problem when in logic I just take functions, say, continued from last point, is the person R honest for the course C at time T? Yes, we could do that and derive in our own logical inferences. However, what you'll see is that, number one, because of this time as the new axis, my number of states, they multiply. Not all may be useful. Number two, in propositional logic, I did not discuss something called as action, which also could technically be defined. Does the roll number R change cheats in course C at the specific time T? However, when I do that, now we're considering interaction between every states and every action possible. So my so-called logic has nothing which my classic search had, which was find out which actions are feasible and only apply those feasible actions to a predecessor to generate the successor. The logic has nothing like that, and therefore they are representational problem, which we so far did not talk about. I'll talk about it right at the end. And therefore what we say is that we have an interesting search with a logic, and that is how I define the happy marriage between the two, which will be agenda for today. Now, per se, this definition itself clarifies everything, because we've studied search, we've studied logic, and I've told you exactly how the fusion is gonna be, which is exactly out over here. Just define the states and actions using propositional logic, and therefore I have less to teach you, and we can directly go on to maybe an example. So let's take in a small example, and I say something that I miss quite a lot is the fact, so say now what would I like to do is I would like to travel from my current place, which is Prayagraj, to say at Delhi, and I need to travel. So there's a person, I need to travel from this place to this place, and this will be my equivalent of an action. Now, obviously what you would like to do is the fact that probably you would like to say that let's generalize it up as much as possible. So you say that instead of a specific place of travel, I say somebody just needs to travel from city to a to city, enough of this coronavirus and lockdowns, and the person P needs to travel. Now this is not a specific action, it's called as an action schema, where the term schema of course is what you have already studied into the courses on software, which says that it's a general template. In this template, you could supply any from airport, any from city, any to city, and who needs to travel, and boom, the action will be executed. That is what I call as my action schema. Now remember, the moment you use the term as schema, you need to be careful about how many actions are there. I can always get an action from an action schema by what is obviously called as substitution. And the substitution of course is the from airport is Prayagraj, the to airport is Delhi, and the person P is RK. If I apply this substitution to this action schema, I can get this specific action. So, if you really want to know how many actions are possible, in India there are probably much more than 1,000 places, let's say 1,000. 2 could also be substituted by 1,000 symbols, places, and P of course is the person. There are obviously a billion of us. Let us just say that the ones who are being driven by my systems are 1 lakh. So if I just write down one action schema by this substitution, it turns out to be 10 to the power of 3, 3, 6, 7, 8, 9, 10, 11. So these many actions, all the actions can be generated from the action schema by substitution. So let's give another example of a substitution and that producing another action schema. Another substitution into action schema that will produce any other action. So I say from substituted by Delhi, to substituted by Prayagraj, and P substituted by me. Again, of course, I will have to return back. It's high time you people start returning back. So this is what is my action schema that I will be using instead of the standard actions, go to Delhi for the traveling salesman problem, or up, down, right, left for my grid search, as well as my 8 puzzle problem. This will be my new definition of action defined as a schema. Now in classic search, we were also doing something which was obvious, wherein we were dealing with a different action function and a different feasible action function. So let's do exactly the same thing over here. Is every travel a valid travel? Absolutely no. So let's define what is feasible travel and what is unfeasible travel. So I write this down again. This is what is the action schema. Now I define when can this action be applied, which is called as a precondition. If the precondition is not met, the action is infeasible, or we say that the action is not applicable. So in order for any person P, which is me, to travel from, which is Prayagraj, to, which is Delhi, of course the person P needs to be at the from place. Otherwise, how will I travel? I need to be at Prayagraj. I cannot be at Delhi and take a train from Jaipur to Chennai or a flight, it's long distance. And of course, you know that in first order logic, there's nothing like domains. Now they are building up such kind of interpreters, but classically everything is symbol, to is symbol, from is symbol. So there is no restriction that I cannot apply a substitution, say travel from RK to RK by RK. I could do that. I could travel from RK to RK by RK. That's funny, but there are no such restriction. I need to restrict that. And therefore, let me do exactly the same thing, which is, I say, from needs to be a valid place, to needs to be a valid place. This is domain checking. And P needs to be a person. So this is my precondition. If this precondition is not met, then the action will not be applicable. In this precondition, effectively only this is the precondition part of it. This is what I call as the domain part of it, just because Prolog doesn't have domain. How do we differentiate between the two? We differentiate between the two by saying that when you talk about Prayagraj, it was a city, it is a city, and it will ever remain a city. Bad example, Allahabad was a city. No longer. Okay, we're dealing with a strictly finite and modeled world. So it doesn't change with time. So these are completely atemporal. So these are global facts which do not affect my planning. And that's what I said previously. So in the 8th puzzle, do I care about the color of the tiles? No. Here, for the sake of having the correct substitution, I need to do it. This is of course something that will change with time. I am at Prayagraj as of now. You don't know when the flights and everything become operative. I may go to Mars or Pluto. So that's what's the precondition. If the precondition is valid, then we call as the action is applicable. If the action is applicable, I'll have something which is called as the effect. So what's the effect of P going from the from place to the to place? P is at the at place. Now, if you just apply this, something funny will happen, which is, of course, that AI does not have common sense, so you need to define that P is no longer at the from place. So, that's a simple example of an action. If this action schema is applicable for a particular substitution from the precondition, you do go into the effect. This is called as the name of the action schema, and of course this is the precondition and the effect of the action schema. It will appear very similar to your C function. So the domain variables are written here. It's place from, place to, person P, and then of course you have name. There are no return type because everything is logical. In every function, you first check that the input is valid, exception handling. And if the input is valid, then of course you go upon the output, which is the effect over here.